Here we have two large Carrier 30RQP air source heat pumps. Air source being the air is taken through and out of the top, and that's where we take the heat from. As you can see, they are completely composite and mounted on anti-vibration mountings, and they sit outside the warehouse, sending heat into the warehouse. So at home, you'll have a fridge with a little compressor at the back that goes dig-a-dig-dig when you move your fridge. That's the compressors, which are behind these sound cabinets here. There's 1, 2, 3, 4, 5 compressors. Also on the top, you can see all these coils and fans. They are the same thing that cools your frozen products, your ice lollies or your fish fingers. That's the top bit, the cooler. And there's a little black box in the center there, which does the heating. And that is the same as the S-shaped thing at the back of your fridge at home. It gives heat out. This air source heat pump is its main energy draw. The COP, the efficiency of the machine and everything is basically the compressors and the fans. The fans are quite small. The compressors are the main electrical draw. Clean energy, replacing any sort of carbon gas or heating. This clean electricity coming through this cable powers these compressors. These compressors will then create the movement of the refrigeration system, does the absorbing and the dumping of heat. So the items that do the cooling, if you like, the absorbing or the air source, are these evaporator coils here. These are capillaries that just interlink into the coils. The air that's drawn from the fans is drawn through these coils and out, and absorbed heat is taken into the system in the evaporator. Okay, so once the air source heat pump machines have absorbed the heat, they put it straight into the water being here. This is the flow on this particular job. The flow is 48 degrees C. Off it goes to do its job, off to the buffer. When the heat's been dissipated into the warehouse, it comes back, and on this occasion comes back at 38. So the water comes into the machines at 38 degrees C, and it goes out at 48 degrees C. These machines will operate down to -5 to create this water at 48 degrees C. The coefficient of performance is based on a ratio between how much this gorgeous machine can absorb out of the atmosphere compared with how much power it actually absorbs to do so. So again, if I use a kilowatt as an example, a kilowatt input to make the compressors go around versus how much kilowatts can be drawn out of the air is the coefficient of performance, the COP. Now the COP, or the energy efficiency, tails off the colder it gets. So some of the selections we do are based on -5. This particular job is based on -5. And at -5, its COP is very efficient. As it goes up to 0 or +2 or +7 ambient air around here, this becomes exceptionally efficient. Once the refrigeration system, once the air source heat pump has generated the heat that it needs to put into the water, you can have an onboard set of pumps. You have a single pump or a duty and standby pump. These just take the heated water at 48 and just deliver it to the system. It can be on the supply or the flow. On this particular occasion, it's on the flow. So the air source heat pump, once it's done its job, will deliver the heat energy to this little black thing in the center. This little black thing in the center is the heat exchanger, or is known as the condenser. It condenses a hot gas into a liquid, the hot gas refrigerant into a liquid refrigerant, all within the refrigerant circuit. That heat is then exchanged across and into the water. The pumps then take it into the building. So another component it's not one of the major components, the major 4 components being a condenser, evaporator, an expansion device and a compressor. But an important item, quite large on this particular machine, is the filter dryer on the refrigerant side. This filter dryer is on the liquid and it keeps the internal refrigeration circuit, which is quite chunky on this machine, and it just keeps it clean. And these are called replaceable core dryers. You just take the end off, replace it with a new core and pop it in. But the compressors on this machine are independently isolated for vibration. The fans not so much, so what you have is you have a potential for a bit vibration. So what we'll have is we'll have anti-vibration mountings on the base of the machine. And I don't know if you notice on this particular machine the different colours, and the colours could have different weight loadings. So when they're delivered, the guys who position the equipment know that the orange is perhaps for a heavier or a lighter, the purple is for a heavier or a lighter. The mechanical system, the water-based side of the system, which is the mechanical contractor usually installs, has various valves. One of the valves through there you might see looks a bit like a steering wheel. That is just to commission and balance the water flow such that the exact amount of water goes through to get the temperature difference that you need. So that whole water system is balanced, and it's a bit like a check valve, regulating valve, just to keep it correct. Defrost, the black arc of heat pumps. During the winter, when it's say -4, -5 out here, air is drawn into these coils at -4 or -5 and is cooled down to -12, -15 or whatever. Any moisture in the space, any moisture in the area will form into ice or frost on these coils. So the machines sense that, and what they do is they go in reverse cycle and defrost that, it melts it off. Unfortunately, they've anticipated how much water there is here, and there's an auxiliary drain system that will go off and take that water away rather than just wet. Say it was -5 or -6 even outside here. These water pipes have a potential of freezing. A potential, not a great deal, because there's usually water flowing through them. But trace heating is a very, very good idea. Very, very fine electrical trace, just to give the water no chance of it freezing. It's a good idea. Another component within this 30 RQP is it's actually not just a heat pump. This particular product could also just be a chiller, giving cold water, for instance, 6 and 12 if it was needed. On this particular application, it's just a heating only, but you still get the reversing valve. The reversing valve is that multicolored brass thing within there, and it can change around such that these start to reject heat and put coldness into the heat exchanger. Air source heat pumps outside have generated the heat, place the heat and heat energy into the water at the desired temperature that we want, and it comes into the building, and it comes into the building on what they call the primary circuit, and this primary circuit comes to the buffer vessel. Mass is good. The more mass you have, the more balanced your system is. Unless it's domestic hot water, which is a slightly different issue, but when it comes to low temperature hot water, mass is good. This buffer is generously sized. It will absorb any defrost. And what I mean by that is when the machines go into defrost, you may get an element of cold water into this, but there's sufficient mass to absorb that cold water before it goes off to the secondary side. So this is the rough heat generator side, and the other side, the secondary side, is the finesse. The two air source heat pumps we've just been talking about are outside. This is what's called the primary circuit. So this is a rotating circuit of water that goes backwards and forwards from the pumps that were so inside the air source heat pumps. And this is a 38 degrees C circuit, and then into the buffer vessel, which is the big tank beside us. And from there we take the secondary circuit, goes off with the hot water. So this heat generating section is called the primary circuit, and this action area is called the secondary circuit. This is just a little pressurization unit with some water, just to keep the system balanced, just to keep it under pressure. Whereas this buffer, primary circuit, secondary circuit. So beyond that panel there, we have the air source heat pumps generating the heat. The primary circuit brings us into this generously sized buffer, and this is the secondary side. So from this buffer, the water is drawn, duty and standby pumps in case one breaks down, and off and away into the warehouse. So you have air source heat pumps, primary side, generous buffer, and then secondary side, controller's finesse, meaning you do whatever you want with this water. The primary side water is simple. So outside we have the air source heat pumps, the rough end, if you like, the primary circuit, which is generating the heat through electricity, efficiently through electricity, through clean electricity, into the generously sized buffer. All buffers should be generously sized, mass is good. From there we'll have the finesse side of it, and the finesse side of it comes into this warehouse, and the warehouse water at the desired temperature, 45 degrees C, 48 outside, 45 through the buffer. We end up supplying feed to these things. These things are SEAT terminal heaters. You take the water in from the buffer at 45, to dissipate heat, correctly sized to get down to base level, so the whole warehouse is heated to suit. So the whole system is water, air source heat pumps, buffer, secondary circuit to the heaters.